Using the methods covered in this course, you can simulate devices used in a broad range of areas, including nanophotonics, sensing, display, photonic integrated circuits, defect detection, and metamaterials. Here are some practical examples of what can be simulated. And in the following slides, we'll briefly touch on each of these examples and talk about the types of results that we can collect for each one. Photonic integrated circuit technology is a growing application area. On-chip photonic components such as waveguides, couplers, ring resonators, modulators, and detectors can be characterized using FDTD solutions. And the S parameters of these components, which characterize transmission and reflection of the component, can then be exported to a circuit-level simulation software like Interconnect, where the system-level design can take place. The Bragg Waveguide is one example of a photonic integrated circuit component that can be used as a wavelength selective mirror or filter. The Bragg Waveguide shown here is a silicon waveguide with 40 nanometer periodic etching. We can use FDTD solutions to simulate a unit cell of the waveguide with periodic boundaries to characterize the bandwidth of the device. It's also possible to account for smoothing of the waveguide corrugation due to the lithography fabrication step by generating the structure shape given the fabrication process parameters, or by importing the shape of the fabricated structure from an SEM image. Here we can see the simulated operating bandwidth of the device matches well with the measured result. CMOS image sensors used to detect light have pixel sizes on the micron scale. This is a cross-section of 1 pixel of the CMOS image sensor, where you can see that the structure is made up of many components, including microlenses, color filters, metal vias, and silicon substrate. The materials of the structure are dispersive, requiring good material fits for broadband simulations. We are able to simulate optical collection efficiency for different incident angles of light, as well as quantities like the crosstalk and point spread function, which characterize light incident on 1 pixel which gets detected by neighboring pixels. In the online knowledge base examples, we also show how to optimize the radius of curvature and position of the microlenses. OLEDs used for displays such as cell phone screens are composed of a multi-layered thin film structure where spontaneous emission occurs in an active layer sandwiched by a cathode and anode. The structure of the layers and any micropatterning added into the structure, like the photonic crystal lattice structure shown here, can have a large influence on the emission efficiency and angular emission pattern by scattering light at the layer interfaces. Using FDTD solutions, we can simulate the light extraction efficiency and emission pattern from the device for different designs. We can also simulate thin conductive films like graphene. In this Graphene Switch example, a strip of graphene acts as a waveguide. A bias voltage can be applied along one portion of the waveguide, which sets the conductivity of the graphene to act as a switch. Here you can see the fields along the waveguide in the on and off state of the switch. Other active devices, like electro-optic modulators and thermal tuning of waveguides, can also be simulated using FDTD solutions in conjunction with the charge transport and heat transport solvers in device. Another common application is the simulation of plasmonic effects. One example of a plasmonic device is a plasmonic lens, such as the Bullseye Aperture. Here, a thin silver film is etched with a pattern of concentric circles with a hole in the center. The circular grading pattern of the etching enhances transmission through the central hole in the film, as it generates surface plasmon modes, and we can simulate the angular distribution and enhancement of the light transmitted through the lens due to the applied patterning. Optical inspection is commonly used to detect defects on wafers by illuminating and analyzing the reflected scattering from a surface. We can use simulations to characterize the scattering for different illumination and collection modes of the system, to optimize parameters of the imaging system, to maximize the measured intensity of the scattering from a defect. The final example here is a microbolometer, which is used for thermal imaging, where the pixels each have a periodic array of structures that absorb power at a specific wavelength range. And each pixel also has a thermistor, which has a resistance that changes with temperature. We can use FDTD solutions to design the structure geometry to achieve the desired absorption wavelength. Here we can see a plot of the absorption spectrum versus the radius of the absorbing periodic disks. In conjunction with device, we can also simulate the transient and steady state temperature distribution and electrothermal effects. And here we have the simulated temperature profile and transient temperature plot.